Hello and welcome back to your stats notes. So today we're going to be looking at sampling distributions, but instead of looking at categorical data, where we're using proportions, we're going to be looking at quantitative data where we're going to be looking at means. All right, we're still talking about sampling distributions. We're still talking about trying to estimate population parameters from our sample, but we're just kind of shifting the type of data that we're looking at. All right, so it says the height of chickens varies approximately according to the N16,5 distribution. So again, that's saying it's a normal distribution with a mean of 16 and a standard deviation of 5. This time, since we know the mean and standard deviation, we will use the computer to produce lots of data. All right, so we're not flipping anything today, and we're just going to use the computer to generate data. So it says, first thing, plot a histogram of 6 heights. So what I have here, all right, is a computer program. All right, and up top here is my normal distribution, all right, that has a mean of 16 and a standard deviation of 5. So when I click this animated button, what's going to happen is we're going to draw 16 people at random, or in our case, 16 chickens at random, from this distribution. All right, so let me hit this right here. All right, and that's showing the values that I selected randomly from this population. So again, if you think of this as all of the chickens in the world, I just grabbed 16 of them, and these are the results that I received. All right, so keeping this picture in mind, let's fill in the notes here. All right, so it says plot the histogram. So what it ended up looking like, and we're just going to do like a rough sketch here. But there was a bar over here, and we had one here, and then one right next to that that was a little higher, and then a low one, and then a low one and a low one, and then a high one, and then a slightly less high one, and then a little space, and a low one, and a second low one. All right. And these are representing 16 individual chickens selected from our population. All right, now in terms of the shape, all right, doesn't really have much of a shape. It's pretty irregular, all right? We're not seeing like any sort of bell curve or anything like that. They're pretty just kind of spread out and all over the place. What is the mean? And then describe the standard deviation. So we're not actually going to calculate it here. But the program does tell us the mean. It's 14.16. All right, so that's our sample mean. Because it's a sample, we use the symbol X bar. All right, and the standard deviation we can just say is relatively high, all right, implying that things are pretty spread out. And then what was your sample size? We used an N of 16. All right, so it says generate random data 2 more times and record the results below. So again, our first mean was 14.16. And now let's do it again. All right, so we're going to bring this in here. And we're going to generate another sample. So I'm going to hit this animated button again. All right, so that's a second sample. And this one had a mean of 16.96. So we can fill that in. 16.96. And if we run it a third time, let's see what we get. So again, here, animate it there. And this time it worked out to be 17.08. All right, so what you're seeing right here is this is evidence of sampling variability. Right? Even though we're taking from the same population, even though we're taking the same sample size, we get slightly different values each time, which is what you would expect. Right? You don't necessarily expect to get the same things every single time. Right? Even if you're taking from the same group, you're just naturally going to get some differences. And that's what we're seeing right here. So it says now we're going to run it a whole bunch, right? And what we're going to basically do is we're going to generate a sampling distribution. All right, now let's keep those terms straight in our head. This is the distribution of sample data, right? This is the individual results that we got from our sample. When we plot all of these, when we plot all the means, it's called a sampling distribution, right? So we're going to create a graph, not of individual chickens, but of these different means that we calculated from each sample. Right? So what I can do here on my little program is instead of doing one at a time, I can have it do 10,000 at a time. So this is me taking not 10,000 chickens, it's me taking 10,000 samples, each that are 16 chickens. Right. Now, what happens down here, this is all of the different means that have been calculated, right? So every single sample had a sample mean, the average height of those 16 chickens, and then I'm plotting those calculated means down here, right? And I could take another 10,000, and it'll keep going, and I could take another 10,000. So, we talk about getting enough samples. Now we've got quite a few samples here. Let's go 50,000, 60,000, 70,000, 80,000, and that's kind of the beauty of a computer, 90,000. There we have 100,003 samples from our population. All right, the 3 are left over from before. So I have 100,003 samples, each of which involves 16 chickens that I measured their height and took an average of all of their heights. So there's the picture that we're looking at, this one in blue here, right? This is all from this population that we started with. And let's see if we can describe it. All right, so first things first, we're going to sketch it. And we don't need an exact sketch here, just kind of the general gist, which was that, it started low, it got higher, it had a peak, and then it went down pretty much in the same fashion that it went up. All right. Now, again, this is our sampling distribution. All right. And we are plotting the means that we calculated from each sample. All right. Now, describing the shape, all right, it's very normal. All right. And by normal, I mean the statistics normal. So like bell curve. What is the mean and standard deviation? All right. This is the mean of the sampling distribution. So it's a mean of all of the means that we calculated. There's a lot of means here. but it's the mean of all of those sample means that we calculated, and we got 16. And what was the standard deviation of our sampling distribution? So it's not the standard deviation of the chickens, it's the standard deviation of every mean that I calculated. And again, the program gives us this, but it was 1.25. And then what was our sample size? It was 103,000 means calculated from samples of size 16. All right, so the sample had 16 chickens in it. We took 100,003 samples, calculated the means. That's what we're actually plotting here. And then it says, what do you notice as you compare the histograms for heights and means? All right. So basically, the individual heights in a sample have way more variability than the means, we'll say the sample means calculated from those groups. All right, so it's the difference between a sample, which is individuals, and then a sampling distribution, which is the calculated mean from each individual sample. All right, now it says, let's see what happens when we increase our sample size up to 25. All right, so I'm going to clear this out. So there goes our 100,000 samples. I'm going to change n to 25. So now we're taking 25 chickens per sample instead of 16. And I'm going to take a single sample. Okay, so there's a single sample. All right, and we're going to kind of compare this to our original single sample. All right, so there was our original single sample that we kind of charted out. There is the one that we just got when n equals 25. So the first point says, compare the sample standard deviation to n equals 16. And I would say the main difference is we have a little more clustering in the center so that things seem less spread out. So we'll say more clustering in the center. So things seem less spread out. I.e., a lower standard deviation. Now it says, repeat the process until we obtain 3 means. So again, looking at the screen here, the first mean on that was 16.03. So 16.03 is our first mean. And then we're going to do it again. All right, so we're going to hit animated again. And this time our mean is going to be 17.2. And we'll do it one more time. And this time we get 16.39. All right, 17.2 and 16.39. And again, this is just evidence of sampling variability, right? We're getting different results each time, right? Because that's going to happen when you take samples, right? You're not always going to get the same results. But notice, even in just these 3 samples here, and again, 3 is not really enough, but in these 3, we only go from a low of basically 16 to a high of 17.2, where here we went from a low of like 14 to a high of like 17.1. So we are seeing that variability is higher when our sample size is low, and it's smaller as our sample size increases. All right, so let's run it a whole bunch again and see what we get. All right, so this is the same sort of thing that we did before, where we're going to generate lots and lots and lots and lots of results. All right, so now I'm going to take 10,000 samples, each of which has 25 chickens in it. I'm going to calculate the average for each sample, and I'm going to plot it down here. All right, so there's 10,000. There's another 10,000. There's another 10,000. There's another 10. There's another 10. We'll get the same 100,000 that we got the first time. All right, so there's 100,003, because again, the 3 we did at the start, means that are being plotted here. All right, so these are 100,000 different means that have been plotted. Right, it can be kind of hard to see over here on the left, but like basically those bars go, the scale on the left goes all the way up to like 38,000, because again, there's 100,000 different means there. So we've got this giant sort of graph here that's plotting every single mean that we calculated. Right, so let's graph it on our paper. And again, it looks pretty much like the first graph that we had. Right, it's not very different. All right, so we've got this right here. We might have a little one here, a little one right next to that. It's a little higher, one that's a little higher still, one that's a little higher still. Then we've got our peak one, and then we basically come down in a mirrored fashion. All right, so there we go. And again, these bars represent the calculated means, from each sample. All right, and the left side here is just a count. All right, it's counting how many there are. I guess I should have probably put that on the other ones. All right, this is basically counting them, and this is like the individual heights of the chickens, versus this one over here is the count. And again, we're still plotting the means that we calculated from each sample. All right, so describe the shape. Still, we can say that this is very normal. All right, that hasn't changed. If I look over on the computer screen here, the mean of our sampling distribution, so the mean of X bar, the mean of our means, is 16. And the standard deviation of our sampling distribution is 1. All right, I'm going to put that heading above this too. Again, the vocab is sometimes the hardest part of this unit. So this is our sampling distribution. All right, what was our sample size? So this sample size was 103,000, not 103,000, 100,003 means coming from samples of size 25. So what do you notice as you compare the histograms for heights and the two different means. So as we compare our three different histograms, kind of what are you finding? What are you noticing? And the first thing I want to draw your attention to is that when we increased our sample size, if we look at our sampling distributions, right, the mean of the means, right, the center of our sampling distribution stayed the same, but the standard deviation changed, which is the same exact thing we saw when we were flipping Hershey Kisses. All right, it didn't matter whether we flipped them 5 times, 25 times, or 100 times. The center of our distribution stayed consistent, but the spread of our distribution, or the standard deviation, decreased as our sample size got larger. We're seeing the same exact thing here, right? Our sample size didn't affect the mean of our means. Again, it's hard to say, but the center of our sampling distribution, but it did affect the standard deviation of our sampling distribution. So what do you notice as you compare them? All right. As our sample size increased, the center of our sampling distribution stayed the same, but the standard deviation decreased. Right, and that's kind of the main takeaway that we want to keep in mind there, is that our sample size isn't going to affect the center of our sampling distribution, but it is going to affect the spread. So we can still be certain that we're zeroing in on the population parameter, but how close we get to that is going to change based on how big our sample size is. The larger the sample, the closer we're going to be on average to the right value. The smaller our sample, the further away we'll be on average. But still, either way, we are kind of averaging out to the right value. All right. 16 says, let's see what happens when we do this with the same thing with the data that's not normal. All right. So we started off here with a population that was normal. All right. So what I'm going to do now is I'm going to change this population. All right. I'm going to make it not normal. All right. So now here is a skewed distribution. All right. Now that skewed distribution, according to the program, has a mean of 12.09 and a standard deviation of 8.27. So what I'm going to do is I'm going to take 10,000 samples from this skewed population. All right, and then I'm going to take 10,000 more, and I'm going to take 10,000 more, and 10,000 more, 10,000 more, and 10,000 more. And there's my 100,000 samples. Now, the program is telling me the mean of my population is 12.09. If we look down at my sampling distribution, you're going to see that even though this was skewed, my sampling distribution still ended up looking normal. And the center of my sampling distribution is at 12.09, the exact mean of my population, right? Which is what we want, all right? That means that we're using an unbiased estimator because the center of our sampling distribution is equal to the population parameter. Now, let's make this even crazier. All right, so I'm going to clear this out, and I'm going to make an even crazier population, all right, that's got like all sorts of crazy weird peaks and so on and so forth. All right, so that could be a population distribution. All right, it's a little weird, but it could be a population distribution. All right, it has a center of 15.59, and I'm going to take samples from that. All right, and I'm going to keep taking samples, and I'll take my same 100,000 that we've been taking every time. All right, and if we look, even though this had a crazy number of peaks and is definitely not a normal population, the sampling distribution that resulted from that still ended up being normal. Right? And this turns out is going to be really, really important. This is going to make our analysis and the number of places where we can apply this analysis way more robust, way more varied, way more diverse, right? Because it turns out that even if our population is non-normal, all right, so even if our population is non-normal and like terribly skewed or has all sorts of weird peaks and does not follow a normal bell curve, that's fine, right? It doesn't have to. It doesn't have to be a normal population, because if we take enough samples from that, the sampling distribution that gets generated from all of those calculated means will be normal. And more importantly, it'll be centered on the true value of the population. So again, I've got this crazy population up here. It has a mean of 15.25. I took 100,000 samples from it. Actually, this time I took 110,000 samples from it. And that distribution that resulted has a center of 15.25, just like the original population did. All right, so this is going to be really important as we move forward, because it gives us much wider berth to use this analysis regardless of what our population looks like. Now, there are going to be some tests that we have to do. There's going to be conditions that have to be met. But as long as those conditions are met, we don't have to care what the population looks like, because we know the sampling distribution will still be normal. All right. So what do we have here? It says, let's see what happens when we do the same thing with the data that's not normal. And basically the end result was, regardless the shape of the population distribution, the sampling distribution, again, that's why all these vocab is tough in this unit. Lots of distributions still ended up being normal. And more importantly, or maybe not more importantly, but importantly, and centered on the population parameter. All right, which is another way of saying that it's unbiased. When it's centered on the population parameter, it's unbiased. All right, so probably would have helped if I'd written that on camera. Sorry about that. So regardless the shape of the population, the sampling distribution still ended up being normal and centered on the population parameter, which is what we refer to as being unbiased. Now, that observation that we just made is really powerful in statistics. So it has a name, all right? And the name for that observation is called the central limit theorem, which states if conditions are met, we'll talk about those conditions in a second, the sampling distribution, which again is all the calculated statistics plotted out. And for our class, the sampling distribution is mostly going to either be means or proportions. Those are the two ones that we're going to be dealing with. Is approximately normal for large n's we'll say sample sizes instead of n's. And then I'll put n in parentheses. Regardless of the distribution of the population. Now, what are the conditions? So they're more or less the same as the ones we looked at last class. they're just going to be sort of slightly different. There's, randomization. You should always be selecting things sort of randomly so that you're not biasing your selection process. You also want independence between the participants, so that you're not taking from like a group that's all going to be in common some way. One person should have no ability to predict what the other person is going to be doing. Each person is kind of independent of one another. For example, if I measure my height, it has no connection on, Miss Gerzafi's height. But if you were selecting all of my relatives, then we wouldn't be independent because they all share some of the same genetic traits. We have the 10% condition, which really relates to sampling without replacement. And again, this one has particular relevance to being able to calculate the standard deviation. All right, so that's where this one comes into play. And then the third one is a large enough sample. Now, this used to be the one that was n times p had to be greater than or equal to 10, and n times q had to be greater than or equal to 10. But we don't have that in this situation. So generally, the rule of thumb that we use is 30 is large enough if the histogram looks, not totally crazy. And 40 is always large enough. Generally, this is the benchmark that we're going to use in this class. So as long as the sample size is 30, we're good to go. And you saw that even 30 is a little conservative because on that computer program we just did, the sample size was only 25, and our distribution still ended up looking really normal. So again, 30 is going to be safe enough for our purposes. So as long as n is 30, we're going to say that we're good to go. All right. Now, the other thing, this really only applies if the population is not normal. All right. If the population is normal, then we don't really need to worry about our sample size. But if the population is not normal, or the problem doesn't tell us whether the population is normal, then as long as n is 30, we don't care. It doesn't matter to us. But if the population is normal, then we don't even have to really worry about it. And again, while this one deals with standard deviation, this one deals with being able to use the normal distribution. So when you want to be able to use the normal distribution, this is where that one is coming into play, where this one's more relevant to like calculating the standard deviation. So if conditions are met, the sampling distribution is modeled by a normal model. So this is basically just saying that, I don't like the way that's written. The mean of the sampling distribution, so the mean of y bar, is equal to the true average, or the population parameter, or we can say the population average. All right. And again, this is saying that the standard deviation of y bar, and again, y bar, x bar, it doesn't matter which letter you're using, but the standard deviation of y bar is equal to the standard deviation of the population divided by the square root of n. All right. Now, where does this formula come from? All right. It comes from what we learned about combining random variables. All right. So when you calculate an average, you add everything up and divide by n. You divide by how many there were. We learned that when you're adding random variables, you actually have to add the variances. So we could think of this as, okay, I'm doing the variance plus the variance plus the variance, dot, 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 plus the variance, and I'm dividing by n. I'm calculating the average variance across all of my samples there. Now, another way to write this would be, okay, this is really n times the variance divided by n. Now, we're not really concerned about variance, we're concerned about standard deviation. So I actually have to square root this. All right. And then if I wanted to put this n underneath the square root, I could rewrite it like this. And then I've got n over this over n squared, because I put it under the square root. Now, these will cancel out. So one n will cancel out with one n down here. And that leaves me with the square root of this over n. And I could actually take the square root of the top there and just be left with the standard deviation over the square root of n. All right. So again, you don't need to know this derivation. I'm never going to test you on where this came from, but it is connected to what we learned about combining random variables. So it's not some crazy made up formula. It talks, it ties back to what we did in the last unit. All right. So now that we have all this background information, let's see how we're going to apply it. Practice. Speeds on the cars of a highway have a mean of 52 miles per hour and a standard deviation of 6 miles per hour, and are likely to be skewed to the right with a view very fast drivers. Describe what you might see in a random sample of 50 cars. So again, this right here is our population parameter, all right, or our population mean, all right. This right here is also a population parameter, but this is our population standard deviation. Now, if we're looking at our conditions, we are randomly selecting cars, and presumably each car is independent from one or the other, right? Just because one person's driving fast doesn't necessarily impact what other people are doing. We are under 10%. Our sample is under 10% of all of the cars on the road. And we are large enough because n is greater than or equal to 30. All right, so all three conditions are met. So our sampling model is saying the mean of our sampling distribution, if we were to take a whole bunch of samples over and over again, is going to equal the true value, which is 52. And the standard deviation of our sampling distribution is going to equal the population standard deviation, which was 6, divided by the square root of our sample size, which was 50. All right. So 6 divided by 50, my calculator here, or 6 divided by the square root of 50. 6 divided by the square root of 50 works out to be 8.5, we'll say, or 0.85, we'll say. So 0.85. All right. So as far as what we expect to see, the central limit theorem tells us the sampling distribution will be normal. That should be an uppercase N, normal. Which means 95% of cars will be plus or minus 2 standard deviations from the mean. Or if we go 2 above and 2 below that, we're basically looking at 50.3 miles per hour to 53.7 miles per hour. right? And that's not talking about individual cars. That's talking about a sample of 50 cars, all right? So these are sample averages that we're talking about here, all right? So across 50 cars, we expect those 50 cars to average out somewhere between 50.3 and 53.7, okay? All right, let's take a look at two more problems and then we'll be done for the day. All right, newborn weights. The weights of newborn children in the US vary according to the normal distribution with a mean of 7.5 and a standard deviation of 1.25. The government classifies a newborn as having a low birth weight if the weight is less than 5.5 pounds. What is the probability that a baby chosen at random weighs less than 5.5 pounds? So this is basically a sample of one. This is n equals 1. If you just choose a single baby, all right? So there's no fancy transformation that has to happen here. This is just saying, all right, if we select one baby from this population, what's the chances that we get somebody that's below 5.5 pounds? All right, so it would just be negative 999 to 5.5, so below 5.5 when the standard deviation is 7.5. Sorry, the mean is 7.5 and the standard deviation is 1.25. All right, so if we go here and we say NCDF, negative 9999, 5.5, the mean is 7.5, the standard deviation is 1.25, and we paste that in, it's going to tell us that it's 0.0548. 0.0548. All right, so there's a 5% chance that a randomly chosen baby is going to be under 5.5 pounds. Now this is saying you choose 3 babies at random and compute their mean weight. All right, so now our sample size has gone up to 3. What are the mean and standard deviation of the sampling distribution of the mean weight of 3 babies? So we know that the mean of the sampling distribution is equal to the population mean, which the problem gives us as 7.5. Right? The standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of n. So basically, you've got your population standard deviation that applies to samples of size 1. And then as your sample size increases, the standard deviation is going to come down. All right, so we're looking at 1.25 divided by the square root of 3. All right, so 1.25 divided by the square root of 3. And we get 0.7217 as our standard deviation. And again, we can use that formula here because even though we're sampling without replacement, 3 babies is obviously going to be less than 10% of all newborn children. Now C says, what is the probability that their average birth weight is less than 5.5 pounds? So that's saying, you select 3 babies. What are the odds the average of those 3 babies is under 5.5, which is different than what we did up here. This was you selected 1 baby, what's the chance that they're under 5.5? This is we're selecting 3 babies, what are the odds that those 3 babies average out to under 5.5, which should be a lot lower, right? Because getting 1 baby that's underweight, sure, it's going to happen. Getting a sample of 3 babies that average out to be underweight is going to be much more difficult. So we should expect a smaller number here. And that's exactly what we're going to get. So the first part's still the same. The mean is still the same. What's changed is our standard deviation, because as your sample size increases, you're going to have things less spread out. So we go from using a 1.25 to a 0.7217. All right. And if we put that into our calculator, we're going to get, so the only thing that has to change here is the 7217. Everything else can stay the same. We get 0.0028, basically, 0.0028. All right, one more, and then we're done for the day. The number of flaws per square yard in a type of carpet material varies with a mean of 1.6 flaws per square yard and a standard deviation of 1.2 flaws per square yard. All right, so right here, these are your population parameters. One for the mean, one for the standard deviation. The population, oh, one thing I wanted to note here. It didn't matter that it was only 3 babies because it told us that the original population was normal. So that's why we didn't have to care about the sample size on that one. 3 is fine because the original population is normal. All right, I bring that up because it says this population distribution cannot be normal because a count takes only whole number values. So is that a problem? Well, it's going to depend on our sample size. An inspector studies 200 square yards of the material and records the number of flaws found in each square yard. To calculate the mean number of flaws per square yard, inspect it. Use the central limit theorem to find the approximate probability that the mean number of flaws exceeds 2 per square yard. So this 200 is our sample size. Is above 30, so it doesn't matter that the population is not normal. And again, that's the central limit theorem that says that. Right, that's what lets us continue on with this, even though it's not normal. All right. Now, as far as doing it, all right, it's pretty much just what we did up here. Right. The mean of our sampling distribution is equal to the population parameter, or the population mean, which means it's just 1.6. The standard deviation of our sampling distribution is where we have to use our formula. So it's the population standard deviation divided by the square root of n, or in our case, 1.2 divided by the square root of 200. All right, which, if we do that, 1.2 divided by the square root of 200 is 0.0849. So 0.0849. And then if we want to know the chance that the flaws exceed 2 per square yard, we're basically just doing an NCDF, which we can do because our sample size is above 30, from 2 to 9999 when the mean is 1.6 and the standard deviation is 0.0849. Right. So we go here, we go to normal CDF, we change it to 2, positive 999, 1.6, and 0.0849. And we get an e to the negative 6th. So we have to remember that that's really 0.1, 2, 3, 4, 5 zeros, and then 1, 2, 3, 1. All right, but make sure that you don't accidentally just write like 1.23. Notice that there's the e to the negative 6 there and what that's telling you to do. All right. So again, very similar to what we did last class. It's just instead of dealing with proportions, we're dealing with means, which means we have a different formula. All right. Instead of using the formula from last class, we've got our new formula when we're dealing with means. We calculate a standard deviation. We get our mean. We use it as part of some sort of NCDF. All right. So if you have any questions about this, let me know. Otherwise, have a great day, and I'll see you when I see you. Bye.